now we consider a special case of surfaces, which is a closed surface. And this type of surfaces is important because the whole Gauss law is actually about closed surfaces. So we assume this closed surface. So this is like it's a sort of an ellipsoid, if you can think of it. Okay, so it's a closed. Think of it as a balloon in this case. And we want to find, and it is placed in some electric field. The electric field doesn't need to be uniform. In general, it is not. It can be any electric field. And as you can see, the electric field lines are penetrating the surface, some coming in, some coming out, and so on. There might be also a source of electric field lines inside the surface, so that's also possible. Now we want to find what is the flux through this closed surface. Of course, the idea would be again to divide this surface into small elements, delta AI, like I'm showing, they are shown here in the grid here. Each of these is a small element, and it's a vector, as you remember. It's an area element whose magnitude is equal to the area, and its direction is normal to the surface. Okay, I'm showing here a few of these, and then find the flux through each of one of these, and then sum that flux or integrate actually over the surface. So this is how we find the flux through this surface. But there are some peculiarities of closed surfaces as far as the electric flux is concerned, and this is what we will be discussing now. So these are the vectors, and these are, as you know, they are perpendicular to the surface. And this is what we write down. This is the flux through the ith area element, which is given by the vector delta AI, which is E delta AI cosine theta I. And we can, you know, if you look, for example, here, theta I is the angle between the vector A and the vector delta I. So if you think of this as E cosine theta I, then actually this means the projection of E along the vector delta AI here, as you can see from here. Okay, so therefore we can write this as En delta AI. En means E normal, the component of E normal to the surface, that is parallel to the delta A here. So you can write the flux through each of these elements as the component of the field at that element perpendicular to the surface multiplied by the area element AI. So you can think of it this way. I mean, this is another way of looking at it. Okay, so now we note that this flux element for each area element can be positive, can be negative, or can be zero. To illustrate this, look at these three figures. Okay, when this depends on what? Actually, this depends on whether the field lines are coming out of the surface. In this case, it is positive. Going into the surface, in this case, it's negative. Or they are parallel to the surface. In this case, the flux through this area element will be zero. Why is this? Now, this is evident here. For example, consider this area element coming from here, for example. The electric field line is leaving the surface, as you can see here, and it is shown here. Now, in this case, E cosine theta, or E normal, is positive because E cosine theta in this case, theta is between 0 and pi over 2, so the cosine is positive. So E cosine theta is a positive quantity multiplied by the area, and the area is a positive quantity. So this, the flux through delta phi through this element in this case, when the field is leaving the surface, is positive. Now, what if the field line is entering the surface? Look at this point here, for example. Here the field line is entering the surface. Now, by definition, for a closed surface, delta A is always out of the surface. This is how we define it. It's always defined to be out of the surface by convention. In this case, when the field line is entering the surface, the angle between delta A and the electric field direction is greater than pi over 2 and less than pi. So the cosine is negative in this case. Therefore, the flux in this case element through this area element is negative. Now, what if the surface is just, you know, passing the surface tangentially, like, for example, here. Here, this is the field line, and this is the area element. The angle between them is pi over 2 because the field is along the surface. It's not penetrating the surface. In this case, cosine theta is equal to 0, and so the flux element through this area element is 0. Therefore, this term, the flux element for a closed surface through each of the area elements can be positive, negative, or 0, depending on whether the field line is coming out of the surface. In this case, it's positive. It's going into the surface. In this case, it's negative, or it's just moving parallel to the surface, in which case you get 0 for this element. And therefore, to find the total flux, as usual, we add up all of these in the limit delta AI goes to 0, which means we integrate over the surface. Okay? Therefore, this summation will have positive quantities, positive terms, will have negative terms, and will have general terms, generally speaking. Okay? And the same applies for this integral. Okay? Now, so this is the meaning of that. So this sum can be positive if we have more positive terms than the negative terms, it will be positive. If we have more negative terms than the positive in the sum, the whole thing will be negative. In other words, if you have more field lines going out of the surface than those coming into the surface, in this case, you will get a positive. If you have more incoming lines than those going out, then in this case, it will be negative. If they are equal, or if the field is not at all going into the surface, in this case, you will get 0. Okay? Of course, remember, note that you might say, okay, but come on, in this case, every field line that is coming in is going out. Yeah, but this might not be true if you have charges inside here that are sources of the field line or sinks of the field line. In this case, not all the field lines that are coming will be going out. Okay, so this is not always the case. So this might be positive or might be negative, and this is of course the essence of Gauss' law, as we will just see. So we write the integral for this integral, which is the integral, which is an expression for the flux for a general field through a general surface. When the first surface is closed, we write it in this manner, and we put here usually a circle, and in the slides we put a square sometimes, but sometimes you put a circle. Sometimes we put an S here to remind ourselves that this is a surface integral, but actually it's evident from the dE here that this is a surface integral. So when you see this sign here, you understand that this is an integral over a closed surface. So this is to tell you that you have a closed surface. So I just summarize what I have said. If for a closed surface, if the number of lines going out is larger than those coming in, the flux is positive, and if the number of lines going out is smaller than those coming in, then the flux is negative. And if the number of lines going out is equal, or if there are no lines going into the surface, in this case, the flux is 0. Okay? So this is an important property of the flux through a closed surface. Now, we call the idea of net flux is actually the net number of lines crossing the surface, which is number going out minus number coming in. So we say the net flux is positive if you have more lines going than lines coming into. So you subtract the number of lines coming into from the number of lines going out. The going out is positive, the coming in is negative. Their sum is the net flux. And finally, we can write this expression in this form by, in this case, we understand the flux through a closed surface as actually the product of the component electric field perpendicular to each dA area element summed over all these elements. Now, time for an example of how to find the flux, and we will consider again a closed surface. In this example, our closed surface is a cube. Of course, in Gauss law, or when you're considering fluxes of closed surfaces on surfaces, these surfaces need not to be real surfaces. They might be hypothetical surfaces. You can think of define any hypothetical surface and try to define the flux through and evaluate the flux through this surface. So consider here a cube with one edge at the origin and is oriented, as you can see here. I have a uniform electric field that is pointing in the positive x direction. The field is in the positive x direction, as you can see. So the field has no component along the y, has no component along the z. Okay, all the components are along the x direction, and the field is uniform. So the value of the field, the magnitude and direction of the field, is the same in space. I want to find what is the flux through this closed surface, which is in this case a cube. Okay, so how to proceed in finding the flux? Well, I apply my relation, and which is this. I start with this. That is, the flux through a closed surface is this integral calculated over the whole surface, which is closed here. However, in practice, I note that I will divide this into, this closed surface, I will divide it into 6 open surfaces, okay, because it's composed of 6 different planes. So, and these are numbered 1, 2, 3, 4, and you have like 5 and 6, of course, that are towards you, and the one which is in the plane of the board. So these are the 6 surfaces. So the line integral in this case, the closed integral, reduces to 6 integrals over open surfaces. Okay, so now, and I note that in this case, if I want to find the flux, for example, through surface 2 here, then this will be 0 through this surface. Why? Because the electric field is always parallel to this surface, because it's only along the x-axis. And whatever you take, wherever your dA here, wherever you take it, the angle between dA and the electric field is always pi over 2. And so when you evaluate this product, you will get 0. So this surface doesn't contribute. The same applies for this surface. The same applies for the surface coming whose dA is out of the page, and the one who is into the page. So the only 2 surfaces, open surfaces, where I don't get a 0 are the one surface 1 and surface 2. Okay, and therefore this surface integral reduces to these 2 integrals for the flux about 2 open surfaces, which are surface 1 here and surface 2 here. Let's look at these individually. If you start with surface 1, then E dot dA, this is surface 1. dA, for all dA here, they are all pointing in the same direction, because this is a plane. And the electric field is also pointing in the same direction. Okay, so the angle between dA and E for all dAs on this surface is 180 degrees. Okay, so you write this as E multiplied by cosine 180 degrees dA. E here is constant because it's a uniform field. And this becomes cosine theta 180 degrees is -1. This becomes this. You take E outside the integral. What remains is, because it's constant, on the integral over dA. What's the integral over dA? Add up all these dAs. Adding up all these dAs means you find the area. And what is the area? It is L square. Okay, so the flux through this is EL square. Now the flux through surface 2, in exactly the same manner, this should be 2, not 1. Okay, so it is just E cosine 0 degrees, because now the field and dA are parallel for all dAs on this surface, and you take E outside the integral, again it is E multiplied by a EL square. Okay, and so this is what you get. So the total flux is minus EL square plus EL square plus 4 zeros. These 4 zeros are the flux through each of the remaining 4 surfaces that I have. We have discussed why it is 0, and therefore the total flux through this closed surface, which is the cube in this case, is equal to 0.